Welcome to the 20th lecture of this course. So, recall that given a vector space V and a subspace W, it is the set of all cosets V modulo W, which we denote by this notation. This is a vector space over F with respect to this addition and scalar multiplication. Then in the last lecture we proved that if V has dimension n and W has dimension m, if we start with a basis of W and extend that to a basis of V, it is just an extension. I do not know what these elements are, just an extension. Then the extra elements that we add here, their corresponding cosets will form a basis of V mod W. Okay. So, that shows you the dimension of V mod W is dimension of V minus dimension of W. Okay, so thus tells you that the dimension of the quotient space, given that the dimension of W V and the subspace dimension of W. Now, I am going to talk about another important role of this quotient space. Recall that, as I have already said, the quotient space can be regarded as the space of geometrically it can be regarded as the space of all translates of W, or somewhat more concrete or more more vivid will be in R V equal to R3 and we start with a plane. So, then V mod W will be the collection of all planes, collection of all parallel planes. Okay. As what I was saying, that now I am going to talk about another very important role of this quotient space V mod W. So, the role is that I am now saying it orally and we will the rigorous mathematical justification will come will follow that. So, this V mod W plays the role of a natural complement as a natural complementary subspace of W. So, the meaning of complementary subspace of W and why I am saying natural, this will be apparent soon. So, first define what I mean by a complementary subspace of W. So, given a vector space, I am not assuming V is finite dimensional, V could be anything and W is any subspace. Then a subspace W prime of V is said to be a complementary subspace okay. So, we will complete the definition later. Let us look at let us go back to something which we have proved a few lectures back. So, in any vector space V and W, if you let us assume finite dimensional, if W1 and W2 are the subspaces of V, then we have proved that dimension of so we have first shown that W1 plus W2 is the subspace, is the smallest subspace that contains W1 and W2, and the dimension of this turns out, so the dimension of the sum. So, this is what we call as the sum of the vector spaces. The dimension of the sum is not the sum of the dimensions, because we need to subtract the dimension of the intersection. Okay. This is what we have already proved. So, but so this is very tempting to consider dimension of the sum should be sum of the dimensions. So, that happens if and only if dimension is that happens if and only if dimension of the intersection is trivial. So, dimension of sum equals to sum of the dimensions if and only if W1 intersection W2 is trivial, right. So, that the dimension of that is 0. So, if this happens, that is for two subspaces. So, let me now we will make a definition in generality, we will come to this later. So, let us first define what I mean by a direct sum. So, given a vector space V, the definition that I am going to set, that is in generality I am not assuming it is finite dimensional. So, the finite dimensional case here I have just considered for a maybe for a motivation. So, the dimension, if V is a vector space over F and W1 and W2 are subspaces of V, then we say the sum is direct. We say the sum is direct if their intersection is trivial. Okay. So, with this terminology you see the dimension formula that we have already proved. So, the dimension of the dimension of the sum is same as the sum of the dimensions in the finite dimensional setup. So, dimension of sum will be sum of the dimension if and only if the sum is direct. Okay. So, we say the sum is direct if the intersection is trivial. So, in that case we denote the sum by this notation. So, this notation is to tell you that this notation just to so what is this object? This object is nothing but this sum. So, but this plus circle that just tells you that the intersection is trivial. And it is very natural to ask whether the notion of direct sum can be extended for finite instead of 2, whether it can be extended for any finite collection of subspaces. Likewise, the sum of subspaces, indeed it can be done. So, suppose I have a collection of for W1 up to Wn of subspaces. So, earlier I can define the sum of these subspaces. I say this sum is direct if so it is very tempting to write that any two intersection will be trivial, but this is not the case here. So, try to follow it properly. If for any I Wi intersection, the sum of other, so Wj j from 1 up to n, j not equal to I, if this is trivial, So, try to understand that this is this, and so this is actually a stronger condition than saying any two intersection will be trivial. Let me give you an example. So, we will come to that later. I need to define direct sum. So, suppose in R2 if my W1 is let us say x axis, so W1 is nothing but the linear span of E1, W2 is y axis the linear span of E2, and let us set a W3 to be the linear span of E1 plus E2. So, geometrically it will be this line. So, this is my W1, this is W2 and this is W3. So, what is the sum? So, sum of W1 W2 you can easily see it is whole R2. Okay. So, because any x plus y, x comma y can be written as x plus 0 plus y 0 comma x comma 0 plus 0 comma y. So, a member from W1 and a member from W2. So, this is R2 and this sum is direct in fact. Okay. Whether this sum, this is not direct, because if you take the because W3 plus W1 plus W2 is actually W3 itself, okay, intersection is a W3 itself. So, this sum, though they are the same subspace, so but here I cannot say the sum of this subspace, this sum is direct. So, the directness, this is at the notion of directness is attributed to the sum of the collection which is under consideration. So, the sum of W1 and W2 is direct, but the sum of W1, W2 and W3, that is not direct. So, when we say direct and not direct, we have to mention that what are the summands, okay. But yeah, as you can see that here also if you take W1 and W2, so W2 and W3, the intersection is trivial, same as W1 and W3. So, this condition is actually a stronger one, okay, because why, okay, yeah. So, what I mean is, even if the intersection if I take any two summands, different summands, the intersection might be trivial, but still the sum may not be direct. This is an example for that, okay. But whether if you have this, then certainly you have the intersection of Wi and Wj for all for any j not equal to I is always trivial, because any member in Wj is also a member in the sum. So, it cannot lie inside Wi unless it is 0. So, this is actually implies that pairwise intersection is trivial, but this is actually a stronger condition. Okay, so, so if this happens for a collection of subspaces, if this happens, then I call the sum of these subspaces as direct. I have given an example, I will give you another example. So, let us since we want to talk about, I mean we are always dealing with finitely many, we are dealing with sums of finitely many subspaces. So, in this example, let us stick to, in this example, let us stick to yeah. So, let V be a finite dimensional subspace. So, dimension V is let us say dimension V is n. So, let be a basis of V, let V be a basis of V. Now, what we do is let us consider a partition of the basis B1, B2, Bk, let us say. So, we take a partition of the basis B into k pieces. So, what does it mean? So, B is the union of B1, B2, Bk, and if I not equal to j, Bi intersection Bj is simply empty. So, so we start with a basis and then we consider a partition of the basis. Now, my Wi for any I, Wi will be L of Bi, okay. Remember, since each Bi is a subset of B, since each Bi is a subset of B, so each Bi is linearly independent. So, the dimension of Wi is nothing but number of elements in Bi, okay. Good. One more thing we should have, yeah. So, now my claim is the sum of the sum W1 plus W plus this Wk is direct. This is my claim. So, first let us see what the sum is. So, the sum, so remember the sum is always a subspace. So, what is this subspace? So, if I take any general vector V from any general vector V in V, then V admits, okay. So, I think for simplicity let us use some notation, let us define Vi as follows, that Vi1 up to Vi Ni, okay. So, that is for each I. So, therefore, N1 up to Nk is nothing but N, and B. So, therefore, B is nothing but Vi, Vini, Vij, where I runs from 1 up to k and j runs from 1 up to Ni. Okay. So, if I take any general vector v from V, then V admits as a V can be written as a linear combination of Vij's. So, let me move it to here. So, given V, we must have coefficients like as follows: alpha 1 1 V 1 1 plus 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 alpha 1 n 1 V 1 n 1. Similarly, such an expression will be there for the basis vectors lying in V 2 plus alpha k 1 V k 1 alpha n k alpha k n k V k n k. Okay. Because this is my basis of basis, I will have scalars alpha ij's like this. Now, it shows that the sum of the so yeah. So, this particular, so this lies in W 1. Similarly, so for any for the ith the if we put the parenthesis like this, so the ith parenthesis, the sum appeared in the ith parenthesis is a member in W I. So, therefore, any vector V admits an expression like this W 1 up to, so any vector V can be written as like this, where the W I is in capital W I. So, here the W I is the, for example, W 1 is this. Okay. So, thus it shows that the sum is nothing but whole of V. So, as a subspace the sum is V, but here the interesting point is not only the sum is direct as well. Why? That is very easy to see. What do we need to show? We have to show that W I for a, if I fix an I, then W I plus, so the intersection, the sum of others lie in, they will be nothing but 0. Okay. The intersection is only trivial, and that is very easy to see. For example, suppose a typical vector here. So, how to show that this sum is direct? That is actually again a routine task. So, a typical vector from Bi, as I said, it looks like it is of the form Vi I 1 Vi k. So, Vi Ni alpha Ni Vi Ni. Okay. So, a typical vector in Wi looks like this, and a typical vector in the sum of other Wj's will look like this. So, how does it look like? It looks like for some coefficients, how does a typical coefficient look like here? Br j V r j, where j runs from 1 up to nr and r runs from 1 up to k, but r not equal to I. Okay. Okay. So, yeah. So, a typical vector in a WR where r not equal to I, a typical vector in WR will look like this. Okay. So, now it is quite obvious why if this happens, then what will be its immediate consequence? You bring everything on the left hand side. So, thus you have a big combination of all Vij's which turns out to be 0, therefore, all the coefficients will be 0. In particular, this alpha I 1 up to alpha I Ni, they will be 0, hence it shows that the intersection, the vector lying in the intersection must be 0. Okay. So, we have thus shown that starting with a basis, if I make any partition of the basis and corresponding to each piece of that partition, if I take its corresponding linears, if corresponds to each piece of that partition, if I take its linear span, then V becomes the then the linear sum is direct, and the sum is equal to the whole vector space V. Okay. The sum is equal to whole vector space V. So, that gives us that gives us an example of a direct sum of subspaces, namely starting with a basis and then you just chop that basis into as many pieces as you want, and corresponding to each pieces you get a subspace and whose sum will be direct. Okay. Now, so what have we seen? We have seen that starting with a basis, starting with a finite dimensional vector space, and starting with a finite dimensional vector space, and the basis of that we chop that basis into several pieces, and that is going to give me a direct sum, that is going to give me the corresponding subspaces, the sum of the corresponding subspaces will be direct. Okay. And not only that, V will be the sum of so in this case we will simply write V is the direct, we will simply write this and say that V is the direct sum of W1 up to Wk, and we call this as the direct sum decomposition of V into Wi's. Okay. So, direct sum decomposition. I repeat, by a direct sum decomposition of V into Wi's, that means the sum of the Wi's will be V and the sum is direct. Okay. So, given with a vector space. So, as I said that I started talking about this example, starting about this as an example of a direct sum, namely starting with a basis. If we chop that basis, we are going to get the sum of the corresponding subspaces will be the sum of the corresponding subspaces will be direct, and V will be the and V is their sum. So, starting with that we get a direct sum decomposition of V. Okay. Now, if you see that the way we have proved the independence, the way we have proved this trivial intersection part, okay, the way we have proved this trivial intersection part, then to prove the intersection part, what exactly we have used is the Vij's, they form a linearly independent subset, right. Because if you remember, how did we do? We take a vector from Wi and say if the vector lies in the sum of other Wj's, then we write them as a linear combination of other Vrj's, and then bring everything on one side. From linear independence we are through. So, therefore, the observation that we have made here, that also goes for goes through if we relax this condition, the condition of a basis, just by saying B is linearly independent. So, the example that we may record it as a proposition. So, if B is assuming everything finite dimensional, assuming V is finite dimensional and and S is linearly independent, if S1 up to Sk is a partition of S, then this is direct. Then the sum is direct. Okay. In particular, when S is a basis, then this will be equal to V. Try to understand the point. The point is, in general, if I start with just a linearly independent subset and then consider a partition of that, then the sum will always be direct, but the sum may not be equal to V. If I start with a basis, then certainly of course the sum will be direct as well, but on the top of that I will get V as a direct sum of Wi's, namely I will get the decomposition, direct sum decomposition of V into Wi's. Okay. So, starting with a linearly independent subset, we get a direct sum. The thing is, the opposite is also true. So, as usual, V is finite dimensional. If I am given a collection of subspaces of V such that the sum of W1 up to Wk is direct, then what we do is we start with a basis of W1. Let us say if we see they write it as W1 1 up to W1 N1 and so on, Wk1 up to Wk Nk. Okay. So, given that the sum is direct, then so we take a basis from each Wi and then simply take their union. This will be linearly independent. So, conversely, so throughout this assumption is there in this proposition. Conversely, if I am given a finite collection of subspaces such that the sum is direct, then we see that these Wi's are obtained exactly in the way stated above. Okay. So, basically this will be my linearly independent subset, and once I, so this will this is linearly independent subset, and these are the partitions of that subset, and the linear span corresponding to each partitions correspond to Wi because I have chosen these as bases. So, it shows that in the setting of a finite dimensional vector space, a direct sum is always obtained in the way that you start with a linearly independent subset and then you consider a partition of that, okay, and then take the linear span of each of the pieces of the partition. And I think I have missed the proof of whether this set is linearly independent. That is a very routine checking, can be obtained similarly as we have done. So, I leave this to you, that exercise, check the linear independence. Check the linear independence. So, again let me tell you, the upshot is starting with in a finite dimensional vector space, you start with a linearly independent subset, chop it into take a partition of that subset, then construct the subspaces which are the linear spans of each of the pieces of that partition, then you will get a direct sum. And if you start, even if you have a direct collection of subspaces whose sum is direct, then you can see those subspaces are obtained by taking the linear span of the pieces of some partition of some partition of a linearly independent subset of V. Okay. And in particular, if we want further that the V is to be the direct sum of Wk's, then S has to be the basis. This is an if and only if condition, that every direct sum. So, every direct sum decomposition of V has to be obtained by from a partition of the basis, okay, and starting with the partition of the basis, then we get a direct sum decomposition of V. So, thus direct sum decompositions of V so direct sum decompositions of V are equivalent to partitioning bases, partitioning the direct sum decompositions of V into subspaces are equivalent to partitioning the basis of V in suitable manner. Okay. So, as I said, we are talking about direct sum. So, let me give you one or two more examples, that some important decompositions. For example, this is a nice one, that remember MNF is a vector space, MNF is a vector space over F. Okay. So, we have two further subspaces. One is the subspaces of symmetric matrices, let us write it as SF, symmetric matrices, and there are skew symmetric matrices. Okay. So, given a matrix A, that can be written as A plus A transpose plus by 2 and A minus A transpose by 2. Okay. So, this is symmetric. So, this A plus A transpose by 2 is symmetric and A minus A transpose by 2 is skew symmetric. So, therefore, you see that this can be written as a sum of these two subspaces, and a matrix which is both symmetric and skew symmetric, that has to be trivial, that has to be the null matrix. Therefore, this sum is direct. Okay. That sum is direct, and then equivalently you can constitute a basis of MNF from a basis of this union a basis of that. Okay. And one more such example, similar example for the space of functions. So, if we consider this space of all functions from R to R, it is a vector space over R, then we can consider the following function, which sends each real number x to f of x plus f of minus x by 2. This is an even function. Similarly, if we consider this function f of x minus f of minus x by 2, this is going to be an odd function. So, their sum. So, the sum of these two functions, if I call them f e and f even and f odd. So, you see that given f is the sum of f even plus f odd. Okay. So, what does that show? It shows that this vector space is the sum of the subspaces of even functions and the subspaces of odd functions, and the function which is both even and odd has to be constantly 0, hence the sum is direct. So, likewise this you have a decomposition of the set of all functions from R to R into, you have a decomposition of that into two subspaces. Okay. So, yeah. Now we need to complete the definition what we have left out here. Before that, let me think that whether we have some interesting examples of some more interesting examples of direct sums or not. So, even skew symmetric and antisymmetric skew symmetric matrices, even and odd functions, and more generally. So, though this is an infinite dimensional vector space. So, here we do not talk about basis in our course, but yeah, this is finite dimensional. Here you see that you can have a basis of this by taking the union of a basis of that, a basis of the symmetric and basis of skew symmetric. Okay. So, so far yeah. So, now since I do not have much time, so let us come into the notion of complementary subspaces. Okay. So, we will erase this part here, hope this is not clear. So, the lesson for this is for a finite dimensional vector spaces, direct sum of subspaces, they are obtained by partitioning linearly independent subsets. Okay. So, a subspace W prime is said to be a complementary subspace of W if the sum of W and W prime is direct and the sum is V, or in other words, if the V decomposes into a direct sum of W and W complement. I repeat, given a subspace W, given a subspace W, another subspace W prime is said to be a complementary subspace of W if this happens. Well, yeah, I think I should have said something. Again, I will come back to this. Suppose a vector space, I also should mention that suppose a vector space V not necessarily finite dimensional, suppose it turns out to be the direct sum of a collection of subspaces. Okay. Suppose V happens to be the, so the suppose the collection of the suppose I have subspaces W1 up to Wk such that their sum is direct and the sum equals to V. In that case, as I said, I will use this notation. So, if this happens, then we will have an equivalent description for that. That also I should have mentioned. What is the equivalent description? It says this happens if and only if every vector V in V can be written uniquely as a sum of the form Wk, where each Wi belongs to capital Wi. Okay. This is, you can regard it as a theorem or equivalent criteria for direct sum decomposition of a vector space W into a collection of subspace into the direct sum of subspaces W1 up to Wk. So, why this is equivalent? That is very easy to see. First of all, assume that the sum is direct, that the V is the direct sum of W1 up to Wk, then every V can be written as a linear, since V is the sum, then every V can be written like this. Okay. Now, you have to show why this is unique, because if V admits another decomposition, if V can be written where each Wi prime is also in Wi, if we have another representation of V as a sum of vectors from Wi, then what we do is we bring everything on the one side, Wi minus Wi prime I from 1 up to k is 0, and then what now we do is Wi minus Wi prime can be written as Wj minus Wj prime j from 1 up to k, j not equal to I. Okay. Wj minus Wj prime, yeah. Since the sum is direct, so this the left hand side lies in Wi, where the right hand side lies in the sum of other Wj's. Okay. Since the sum is direct, both the sides will be 0, therefore, Wi will be equal to Wi prime for any I. Fine. So, that shows that the representation is unique. Okay. Yeah, that shows that the representation is unique, and on the other hand, that is also very easy to prove that if each V can be written uniquely as a sum of vectors like this, then the sum will be direct. Why so? So, that is also quite obvious. So, now I am assuming that every V admits a unique expression like this. So, from that I have to show that the sum is direct. First of all, each V can be written as a sum like this. So, that shows V is the sum of Wi's. Now, we have to show that the sum is direct. For that, what do I have to do? In order to show the sum is direct, what I have to do is for any I, let us consider that the vector xi lies in this intersection. Therefore, x can be written as a sum like this, j not equal to I, where Wj lies in Wj. Now, you bring everything. So, now you have the uniqueness of the representation. Okay. So, this x can be written, admits two different this x admits to different representation. One representation is like 0 plus 0 plus 0, only the ith place will be x and else will be 0. This is one representation, x at the ith place, and another representation is there, that is w1 plus 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 wi minus 1 plus 0 plus wi plus 1 plus 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 wik. So, this we have to say x has these two representations, and from the assumption that this representation is unique, it follows that all wi's will be 0 and x will be 0. So, that shows the intersection is direct. Okay. So, that this establishes the uniqueness, and yeah. So, therefore, from now onwards, if I need to show that V is the direct sum of two subspaces, then we know that it is enough, it is equivalent to show that every vector V in V capital V can be written uniquely as a sum of So, in view of this, what this means is every vector V can be written uniquely as a sum of elements from W and W prime. Okay. What is an example of an complementary subspace? This is, so this can be regarded as an example that this is a, suppose this is my V, this is my W. So, this can be regarded as a W prime. Okay. And maybe one more example I should have given, the example that I have already rubbed. So, suppose V is my R2, and W is, let us say, the x axis, then and so we go back to our original example, this is W1, this is W2 and this is W3. It is easy to see that if both W2 and W3 are subspace R, both of them can act as the complementary subspace of W1. Okay. Can act as the complementary subspace of W1. Okay. So, now let us come to the main point of today's lecture, and with that I will finish. Then what is the purpose of, as I said in the beginning, that W prime works as the W prime plays the role of a natural complementary subspace. So, recall that so now suppose V is a finite dimensional vector space, and W is a subspace of V. So, you start with n length W1 up to Wm is a basis of V. We extend that to a basis of V. Okay. So, this is a basis of V. So, the span of W1 up to Wm is W, and let us consider the span of this to be W prime. Okay. So, since this is a partition of the base of a basis of V, so we have the direct sum decomposition. So, thus what you see is given V and given W, an invariant given V and given W, a complementary subspace W can be obtained by taking the linear span of the extra vectors when you add the base, when you add this basis of W to a basis of V. Okay. So, we fix this basis of V, and W, extend that to a basis of V and take the linear span of the extra vectors, you get a complementary subspace, and the rest is also, the converse is also obvious, that suppose I have a complementary subspace of W, let us say I have a subspace W prime such that V equal to W direct sum W prime, we take a basis of W prime, and already the basis of W is fixed. So, like already said that if we take the union of these two bases, we get a basis of V. So, thus starting with a complementary subspace, starting with a subspace W, its complementary subspace can be obtained. So, yeah. So, that is what I was talking, that the complementary subspaces are obtained by extending the basis of W and taking the linear span of the extra vectors, and yeah, and all complementary subspaces are, can be achieved like this. Okay. So, I will finally finish with the correspondence that suppose W prime is a complementary subspace and let U1 up to UR be a basis of W prime. So, try to understand, now I am starting with a complementary subspace, let be a complementary subspace. So, since I have said that is complementary, I have already said as well that whenever I have a complementary subspace, I add the basis of the subspace with this fixed basis and get a basis of V, and whenever, so therefore, this is yeah. So, and from the earlier discussions, since V1, V2, Vm and adding these vectors is a basis of V, or this is then basis extended, is then basis. So, this is an extension of the basis of W to a basis of V, then U1 plus W up to UR plus W is a becomes a basis of V mod W. V mod W. Now, I leave the following thing, just a minute, just a minute. So, yeah. So, try to have see the similarities that in one hand you have W prime, on the other hand you have V mod W. So, if you so a typical element in W prime will look like this, x1 u1 plus 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 xr ur. So, this representation is unique, right, because the u1 up to ur is a basis of W prime. So, the scalars are unique. If I send this to the following x1 u1 plus W plus 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 x r ur plus W. So, this is a map actually from W prime to V mod W. Then this map also satisfies a property, this map also has a nature which is similar to something that we have already witnessed, namely if I add two vectors here and then send it to their images, then if I add two vectors here and then send it to its image by this map, it is same as for sending them to their images and then add. Similarly, for scalar multiplication. So, I leave this verification to you. So, that is the meaning of. So, this shows that this complement, the V mod W is essentially similar to any complementary subspace of W. So, since the given W is the choice of complementary subspace is not unique, because you can extend it in, you can have several extensions, but one thing that we can see that whatever complementary subspace you choose is essentially, so V mod W is essentially like that. So, hence we say that V mod W is plays the natural role of a complementary subspace of W. With that I will finish. Thank you.